Stability of alkenes. Influence of substituents. Alkyl substituents on the double bond influence the relative stabilities of alkenes due to steric and stereoelectronic factors. Example: trans-2-butene is stable over cis-2-butene by about 1 kilocalories per mole. Cis-2-butene suffers from steric strain due to the direct interaction of the methyl groups in space due to their proximity, making it less stable than trans-2-butene. Trans-2-butene has a heat of hydrogenation of 27.62 kilocalories per mole, whereas cis-2-butene has a heat of hydrogenation of 28.62 kilocalories per mole. The more stable a molecule is, the less heat it will give upon hydrogenation. Influence of substituents on the sp2 carbons on the stability of alkanes. Hits of hydrogenation data shows that the more substituted alkanes are more stable than the less substituted alkanes. 2-methyl-2-butene, which has 3 methyl substituents, is more stable than 2-methyl-1-butane, which has only 2 alkyl substituents on the double bond. 2-methyl-2-butane gives out less heat upon hydrogenation than 2-methyl-1-butane, establishing their relative stabilities. Hyperconjugation and stability of alkenes. The greater stability of substituted alkenes is attributed to an electronic factor called hyperconjugation. This can be visualized as an overlap of the sigma orbitals of the CH bonds of the substituent with the pi orbitals of the alkene, resulting in the delocalization of electrons. This leads to greater stability of the system. The more substituents there are, the more the hyperconjugation and greater the alkene stability. The first member of the alkene family, ethylene, and all alkenes contain a CC double bond consisting of 1 sigma bond and 1 pi bond. The bond dissociation energy of the double bond is 144 kilocalories per mole. While the sigma bond is stronger than the pi bond, it is not clear by how much. Each carbon in ethylene is in sp2 hybridization state and the molecule is flat with all atoms in the same plane. The electron density in the sigma bond lies in the internuclear area, whereas the electron density on the pi bond lies above and below the plane of the molecule. Degree of unsaturation in alkenes. The general molecular formula for an alkane is CnH2n plus 2, and for an alkene CnH2n, and for a cyclic alkene CnH2n minus 2, as illustrated for hexane, 1-hexene, and cyclohexane. Compared to hexane, hexene has 1 degree of unsaturation and cyclohexane has 2 degrees of unsaturation. The total number of double bonds and rings in an alkene would be its degree of unsaturation. Calculate the degree of unsaturation in a molecule with a molecular formula C4H8. From the general molecular formula for saturated hydrocarbons CnH2n plus 2, the molecule is missing 2 hydrogens, so it has 1 degree of unsaturation. The molecule could be either a ring or have a double bond. Among many, 1 and 2 are 2 possible structures.